So Barak, go ahead and take it away.
Thank you. Thank you, Lucas. Hello, everyone. Today I'm going to talk about feedback-driven site channels for networks applications. This is joint work with Nico Rosner and Tevfik Bultan. And first, I'm going to introduce and motivate about the problem. Then I'm going to talk about feedback-driven site channel analysis and how we evaluated our proposed approaches, and then conclude the talk. So the side channel vulnerabilities are resource-rigid vulnerabilities in modern programs leaking secret data. Some examples are Meltdown and Spectre, where a malicious eavesdropper can observe the resource usage to read kernel memory or exploit the speculative execution to get user information. We're interested in discovering software side channel attacks. These are usually CPU level side channel attacks, and we're interested in side channel attacks on the network, where let's say two users are communicating over the network. They're going to send packets to each other, and an eavesdropper cannot see the contents of the packet because it's usually encrypted, but they can still observe the size, timing, and direction of each packet. And using that, maybe they can get insight on what the users are doing. So let's say we have an example health application where a doctor uploads the patient's health records with some actions, and the server sends the encrypted test results. And you need to test the app extensively to find any correlation between the observables, the packet sizes and timings, and the user's secret properties, such as like user's gender, user's age, etc., the patient's age, etc. So with 100 inputs, maybe we can profile the system 100 times and get such distribution where the gender property is leaked with the size of packet 29. But this may be an undersampling where with 1,000 inputs, we may get a more accurate input where there's actually partial leakage and not full leakage. So we need to test the app extensively, and we need to generate valid inputs because we're not interested in finding bugs or crashes. And we need to guide the input generation to discover new behaviors instead of being stuck in the same behaviors. So Autofeed is a black box feedback-driven automated side channel analysis tool for networked applications, where the user provides a set of seed inputs and mutators, where mutators take a valid input and generate a valid input. They give an interaction scenario for the input, such as they log into the server, they upload a file, they send a message to their friend, and they choose a sequence of interest. They set the time, budget per iteration, and repeat transfer input to account for noise. And once the user runs Autofeed, it quantifies and ranks the leakage estimation of each feature, meaning that for each feature, it's going to say how many bits does it leak using the Shannon entropy for a set of features using the size of packets and timing of packets. And it also automatically guides the input generation starting from a small seed and mutators, generating more inputs, running those inputs, generating a feature ranking, and guiding the input generation until the leakage estimation converges. So our main algorithm takes a seed set, a mutator set, a number of inputs to generate within a single iteration, where we generate n new inputs using the initial seed set and mutator set. We run application with the seed set and the input set and capture network traces. And then we calculate weights for the mutators using the inputs obtained so far, using the, which I'll go more into detail. And then until the leakage estimation for top n features stays with an epsilon bound for k steps, we're going to generate new inputs using the weights now. We're going to run the new traces, and then we're going to calculate leakage estimation over all traces. And then we're going to do this loop until the leakage estimation converges. So to motivate for weights, let's think of an application. This is an application from one of our benchmarks, where the user uploads an air traffic route graph, and this application returns a web page showing all the plane routes with statistics such as like daily cost of running all those airplanes. And with multiple mutators, you can modify the same route graph in different ways, such as you can have a mutator that adds the new flight routes, or a mutator that changes the airport names. And we need to find mutators that change the input fields that affect either the observables or the secrets to gain new insight on the program behavior. So we start with an input set and mutator set. And for each subset of mutator set, we generate new inputs where each original input has a mutated counterpart, so that an input has a mutated counterpart. We run the original and new inputs where we obtain traces for both pairs, and then we extract features. Let's say the feature we're interested in this case is size of packet 1, but in this case, it's 400 bytes for one, 1,000 bytes for the other. And the weight is actually proportional to the feature value. So this formula is hard to explain, but what you need to know is it takes the feature value difference into account. And also it uses the Iverson bracket notation to denote that if the original input and new input secrets are different, it's gonna return 1, otherwise it's gonna return 0, which means we weigh the mutators that cause the new input to have different secrets or different observable values. And then we normalize all the weights so that they add up to 1 for probability purposes, and return the weight vector W. And this is another example where instead of this, where we have 400 bytes for the mutator 2, so that there is no difference. So to quantify information leakage, we use Shannon entropy, which denotes the initial uncertainty, which is only defined using the terms of probability distribution of secret, and remaining uncertainty, which means the uncertainty we have after observing the feature value, observable value, and the difference of that reveals how much information we gain about the secret by observing feature B. And to accurately estimate this, we need to estimate probability distribution we need to estimate this probability distribution, or the inverse of it, P of V given S. So we use kernel density estimation for it, where it's a probability estimation technique that fits a kernel function over data, and it does not assume the data distribution, and which is a parameter H bandwidth that affects the fitness of estimates, so that if we had 100 points generated over this reference distribution with 0.05 bandwidth size, we get a very noisy estimation. With 0.1, we get a more closer, 0.3, 0.4, we get a much closer. With 1, we get almost the identical distribution, but on increasing doesn't help after a certain point, where with 5, bandwidth 5, we get a much wider distribution, which doesn't capture the actual distribution. So we need to estimate and find the ideal parameter to accurately capture the probability distribution, which we do using the hyperparameter search. We use grid search with k-fold cross-validation, where we test a set of candidate bandwidths. For this example, we show a k-fold cross-validation with k equals 5, where we divide the data set into 5 pieces, and we use 4 of them for the training and 1 of them for the test. We use the training set to fit the KD and estimate the probability distribution. And we get a likelihood by testing the distribution over the training fault, the validation fault, test fault. And we do this for every combination, so that every subset is tested at test. And the sum of it is our likelihood score. And we select the candidate bandwidth that has the highest score, meaning it represents, it's able to fit on this distribution the best using only a subset. We also expand to evaluate our approaches. So we evaluated on 5 example functions and 14 full applications from DARPA Stack benchmark. We aim to evaluate leakage quantification using different probability estimation, mutation weighing heuristic that we propose, stop criterion that we have to stop the iterations, and performance under realistic network conditions. So we crafted 5 example functions where you can think of them as a black box, which take an input and return an observable value. And we crafted these to capture interesting input to observable relations. And one of the reason is we have ground truth on how many bits these distributions leak. So we can accurately estimate how close we are to the actual distribution. And for probability estimation methods, we compare histogram estimation with a small bin size, Gaussian estimation, KD with a small bandwidth, KD with a rule of thumb bandwidth, which is commonly used based on standard deviation. And what we use, KD with parameter search. And with first example, the function returns a random floating point where it is not related to the secret field S at all. So it has 0 bits of leakage. Gaussian, KD with parameter search, and KD with standard deviation is able to converge instantly to the ground truth. But histogram and KD fix converges very slowly because of the small window size. For example 2, the return value is secret padded with some noise, but the noise is, if you chart all the observables, there is actually one-to-one mapping between all the observables and all the secrets. So they're going to this 4 out of 4 bits. And Gaussian and KD with standard deviation can't converge because the feature distribution is actually not normal. It's like a sawtooth. And KD fix and histogram is able to converge instantly because they already assume small window sizes. And KD parameter search starts with 0 bits estimation, and with more and more inputs generated, gets converges to the ground truth. We're also going to evaluate mutation methods, where we evaluate the KD parameter search with weighing and without weighing. In this case, ground truth is 2 bits, where it only leaks the secret when the X parameter is even. So it's an interesting input relation. And only input fields S, X, and Y are affecting the observable value. With weighing, we are able to get much closer to the ground truth compared to not using mutation weighing and randomly generating inputs. Same goes for this, where only X and Y are affecting the observable. And with weighing, we have almost a bit of difference in our estimation compared to without weighing. And in this case, the secret is number of elements, and the return value is the string version of the list, where there is still some correlation, where lists with a higher number of elements have longer strings, but the leakage is not full. So we calculated it with 2.21 bits, and mutation weighing gets the estimate much more closer compared to the without using weighing counterpart. We also use DARPA Stack Benchmark, which consists of 7 applications with known side channel vulnerabilities imitating real-world applications, such as air traffic control systems, social messaging network, or an online bidding website. And we also wrote some mutators shown on the right, such as like adding a car for a rail yard or adding cargo, which represents the different input dimensions. And these applications also have variants, and DARPA doesn't give a numerical ground truth. It just says a vulnerability is present in that application or absent, where our approach has higher leakage values for the present cases compared to the mitigated or absent cases. So the leakage value is consistent. We are also able to converge the estimation within at most 20 iteration with at most 5 hours in almost all cases except one. We also tested the Stack platform is a very controlled platform. So we also tested it with high network noise, where the servers are in like California, New York, or in Moscow. And still the cases where leakage while vulnerability is present have higher leakage rates than the cases where leakage is absent. Because of the network noise, the numbers drop a little, but we're still able to detect and quantify leakage under realistic network conditions. So to conclude, we showed how we observed side channel measurements on the network. We showed how we generate the inputs and guide the input generation to get more accurate results, and also guide the probability estimation to get more accurate probability estimation. And combining all of these, we are able to, over time, we are able to generate interesting inputs and get accurate results and get to the ground truth in the evaluations we had. Thank you.
All right, thanks, Barak, for an interesting, excellent talk.
Thank you.
If there are any questions, please post them in the Slack, and I will read those questions out. I don't see any questions currently, so I have one question.
Okay.
So you talked about how when you run this on servers that are very far away, so there's a lot more network noise going on in between.
Yes.
Are you still able to observe more leakage in the leakier or more insecure applications? But I'm curious about how, if that was done like with a constant budget, or if you just increased the budget very, very high, if you would still be able to achieve the same amount of leakage that you would get on servers that were very close with less noise.
I think with servers with far noise, you're bound to get lower leakage, well, at least in some applications, because like at least in these cases, the leaking feature depends on the timing. And with higher noise, you are able to like distinguish less. If this also assumes that you get the observable once, so that the user does the action a single times, so that you are able to detect it on a single guess. But if the user did the same action multiple times and you captured all those, maybe what you did would happen where you would still have higher leakage, even in the noisier network conditions.
Okay. Yeah, thanks. So we have another minute or two for any other questions. So if there are any further questions, I'll wait maybe a moment to see if anything shows up in the Slack. And in the meantime, maybe we can ask Barak to stop screen sharing.
Okay.
Mohanad, or we can prepare to show the video of Mohanad's talk. All right, so seeing no further questions, thanks Barak for your talk.
Thank you.
Go ahead and introduce Mohanad. We're actually going to play a video. And so Mohanad Al-Hanahana will talk about scalable analysis of interaction threats in IoT systems, and then be available for questions afterwards. So we can go ahead and roll the video.
Hello everyone, my name is Mohanad Al-Hanahna. Today I will be presenting our paper, Scalable Analysis of Interaction Threats in IoT Systems. This is a joint work with my colleague Clay Stevens and my advisor, Dr. The number of IoT devices is growing, therefore it is expected by 2025 the number of connected IoT devices will be increased by 145%. However, this increment in the number of IoT devices comes with safety and security issues where attacker can unlock doors, tamper with the temperature, and get access to Wi-Fi devices by exploiting vulnerable smart home devices. So this raises the question, what makes IoT apps so vulnerable? To answer this question, we need to understand the smart home environment. Therefore, let's have this scenario where we have lamp, overhead light, and light sensor. Those devices will be controlled through SmartThings IoT applications. SmartThings is a well-known platform for automating smart home activities. The first application is IFTTT, if this, then that. This is a third-party cloud provider for automating IoT applications. This application will be triggered when the brightness is changed and will be switching off the overhead light. The second application is a Groovy application. It's called multi-switch. It's provided directly by SmartThings. It will be controlling the lamp and the overhead light. The third application is in the format of IFTTT as well, and it will be switching on the lamp when the overhead light is switched off. Also here, the lamp and the overhead light, when they are switched off, this will be affecting the light sensor. As you can see, we have physical and cyber events that are used for the interaction between IoT apps and IoT devices. To understand the interaction in this smart home environment, let me explain the architecture of IoT, where we have cyber space that has several cloud providers. Each cloud provider provides IoT applications. Each IoT application consists of behavioral rules, and each rule is formalized as triggers, conditions, and actions. Those actions will be sent out to the physical environment where we have actuators and sensors. The actions will be sending commands to the actuators. The actuator will be executing those commands. This will be affecting the IoT environment and generating new events that will be triggering new behavioral rules. If we apply this concept into our example here, we can see the IFTTT application at the top will be triggered when the brightness is changed. Then it will be sending switch off command to the overhead light. At the same time, the switch off command will be sent to the multi-switch because it's also controlling the overhead light. Then it will be sending two switch off commands to the overhead light and the lamp. This also will be changing the brightness and will be affecting the light sensor. At the same time, this will be triggering the IFTTT rule because the overhead light is switched off, and therefore it will be switching on the lamp. According to this scenario, we can observe several issues. The first issue here is the interaction between the IFTTT application at the top and the multi-switch Groovy application. We can see there is an infinite loop of interaction between those applications, where switch off command will be sent repetitively to the overhead light and the lamp. The second issue here is the interaction between the Groovy application and the multi-switch and the IFTTT rule at the bottom, where conflicting commands will be sent to the lamp. Safety and security has been studied in the state of the art from different angles and different perspectives. In general, we identify three major limitations in prior work. They are constrained in terms of either considering physical space or cyberspace, but they don't consider both. The initial configurations of the IoT applications are manually identified. There are compatibility issues by considering or focusing on certain IoT platforms without performing cross-platform analysis. Therefore, some unsafe interactions will not be detected. Therefore, we need to have a scalable approach where we consider interaction of in the cyberspace and physical space, exploring all configuration space, and performing cross-platform analysis. Therefore, our insight to perform compositional and scalable analysis to detect interactions between IoT applications. The first step we performed, we identified the interaction threats, all potential interaction threats that will be leading to threats due to the interaction between IoT devices. We identified two major interaction threats: direct interactions and chain of interactions. And under each category, we identified a subset of interaction threats. So in total, we identified 5 types of interaction threats. We formalized those interaction threats in our paper. You can find the details. But here for the presentation, I'll be focusing on the interaction threats that I'll be showing you here based on our illustrative example. The first interaction threat, we call it action-repeat, where the interaction between the IFTTT application and the Groovy application will be sending switch off command to the overhead light. continuously. And the second interaction thread is called action, where conflicting actions will be sent to the lamp. After identifying those interaction threats, we propose our IoTCom approach that can detect all types of interaction threats. IoTCom expects as input a set of IoT applications, and it tries to identify all potential unsafe interaction between those applications. IoTCom consists of two components. The first component is behavioral rule extractor, where we perform static analysis for each application independently and individually. Then we formalize those applications and provide them to our formal analyzer, where we perform bounded model checking. Therefore, through the combination of static analysis and the lightweight formal analysis, we can provide the scalability and the compositional analysis. Now I'll be focusing on the first component, the behavioral rule extractor. We perform three main steps: building ICFG, converting to BRG, and generating rule models. For building ICFG stands for Interprocedural Control Flow Graph. We perform static analysis over the AST graph. Then we generate CFGs for each method in the IoT application. Then we connect those CFGs together by constructing the call graph to have this ICFG. Now let's have this idea. Let's have this example. We have from the multi-switch application. The subscribe statement here represents a trigger of this application, which will be invoking the lights off method. Then we generate the CFG of this method lights off. After generating the CFG of this method, we perform the same steps for the other methods in each application. And then we connect those CFGs together by relying on the call graph to generate the ICFG. After generating the ICFG, we convert this ICFG into BRG. Basically, here we're identifying the APIs that is related to our analysis and will be affecting the IoT environment. And here we are relying on SmartThings documentation for identifying this set of APIs. As an example here, let's for the lights off, this is the CFG. We iterate each node and to generate the BRG nodes of each node in the ICFG. Here, then we iterate each statement. For example, the timestamp will not be used, therefore we discard it. The second statement is a conditional statement, therefore we convert it into conditional node, conditional BRG node, and then we converted it into three tuples: device, attribute, and value. Those tuples are required by our formal analyzer, as I will describe later on. Then we do the same steps with each node and we annotate each node based on its type. For the false branch here, it does not contain anything that will be affecting the environment. Therefore, we discard this branch. Then we perform the same step for the second method here for this CFG of turn off lights. We generate the corresponding BRG nodes. Then by the end, we will have this graph where the BRG graph where we have identified set of triggers, conditions, and actions based on the IoT architecture that I described previously. For trigger, we already extracted it from the subscribe statement. If you recall in the code snippet, we have here three conditions in this rule. And we have here one action. Then we convert those triggers, conditions, and actions into the formal specifications that are required by our formal analyzer. For the formal analyzer, we provide the formal specification for our IoT applications. We also provide for the formal specification of smart home model and the safety and security properties that we want to verify. So our formal analyzer, we used Alloy. It performs lightweight formal analysis by automating the analysis of converting the predicates into SAT solvers. Then it verifies whether the properties are holding or not. Here I will be explaining the main specification of our smart home formal model. We have first component, a set of IoT devices. Each device consists of several attributes. The attributes maintain different values. And the second component here, we have set of IoT apps. Each app consists of set of rules, and we formalize the rules as trigger, condition, and actions, which is the IoT architectures that I described earlier. And we formalize the triggers and conditions and actions based on the three tuples that I mentioned in the BRG graph. Basically, those tuples are reflecting the devices that will be performing the activities. Now the third component, which is the physical environment, where we have connection between sensors and actuators over certain physical channels. And for identifying those channels and the corresponding actuators and sensors, we relied on heuristic analysis based on prior work to identify those information. Now for the IoT, the specification of the IoT applications, as you can see here, we generate the specifications individually and independently of each other. Therefore, we can fulfill the requirement to perform compositional analysis. Here I'll be showing the first assertion that we used for verifying whether we have action, repeat. And here is the second assertion that we used for identifying action, conflict. We provide all this information to our Alloy analyzer. Alloy will be using off-the-shelf SAT solver to verify the safety properties are holding or not. And based on that, it can generate counter examples. Alloy here is a lightweight tool to perform bounded model checking. Therefore, we can achieve scalability. Then by the end, for our illustrative example, Alloy can identify the two violations that we have, the action, repeat, and the action, conflict. For evaluating our approach, we perform several experiments. In the first experiment, we compared the accuracy of IoT-COM in comparison with Soteria and IoT-SAN. We used publicly available benchmark applications. And we also developed 3 benchmark applications that are also available on the website of our project. Those 3 applications involves interactions by threats over physical events. The purpose of this to verify the capability of our tool in comparison with the other tools. We computed the accuracy based on the test cases that we have. We can see IoT-COM can outperforms IoT-SAN and Soteria. Basically, IoT-SAN and Soteria are missing cases because they don't have the capability to detect interactions over physical space. For evaluating the performance of IoT-COM with real-world applications, we use 2 datasets consist of Groovy and IFTTT applications. We divided them into 622 non-overlapping bundles. Each bundle consists of 6 applications, and we used 36 safety properties. In total, we detected about 2,900 violations. This is the distribution of those violations. The majority are from action trigger with the percentage 35. And in second place, we have action with our repeated or conflicting actions. In the third experiment, we analyzed the performance of IoT-COM in terms of required verification time in comparison with IoT-SAN. We used 11 bundles of real-world applications. On average, IoT-COM outperforms IoT-SAN by 92% without sacrificing detection capability. Finally, this work can be extended by considering contextual information like number of rooms and different floors. In the smart home model, synthesis can be considered for automatically generating safety and security properties. Enforcement can be applied to prevent unsafe interactions. In summary, in this work, we are addressing the safety and security concerns that are resulted by the interaction between IoT applications and devices. First, we identified the interaction threats between IoT applications and devices, and then we propose IoT-COM for addressing and capturing those interaction threats. Finally, we show the capability of IoT-COM, and we evaluated IoT-COM from different perspectives, and we show how it can outperform existing techniques. Finally, thanks for listening, and I would be happy to answer your questions.
All right, thanks so much, Mohammed, for an excellent talk. So we have a couple minutes for questions. There's currently one question in the Slack. I'll go ahead and read that. So from Nico Rosner, he asks, how do you determine the bounded sizes of the relational domains? Have you seen real-world cases where these bounds become critical toward finding or missing a violation?
If I understood correctly here, bounded, so we identified the bounded in different aspects. One thing is that the number of application per bundle. So in each bundle in the real world application, we used 6 applications. So this is the first aspect. So the second aspect, we have different relations that we identified in our paper. So, and our approach can identify those relations. There is no bound. So, and this is one of the reasons why we used Alloy for doing the formal analysis, because it has the capability to capture chain of interactions without being constrained to specific bound in terms of number of relation or in terms of number of applications.
Okay, so there's
I hope this answered the question.
Yeah, so the follow-up was, this is a bounded model checking, right? So I guess we kind of addressed that. So we have another minute or so. If there are any other questions. So I have a question. So I noticed that in your, in the sort of example that you had things like if off time is greater than 7 minutes, but maybe I just didn't quite catch it, but it didn't seem like that type of temporal information is included in the model. Is your model able to capture temporal information? Because maybe like hearkening back to your example, I might not care if there's a action, repeat, if it's separated by like 12 hours or something. So how does your model address those issues?
So the way how we model time in Alloy at this moment, basically we consider the time as this time. So if there is, and then we have values before that time or less or more than that time. So this is how we model the time. So basically we have this value, and if it's, and we check the status if the values are more than this time or less than this time.
Okay, so you could
so it's not temporal.
Yeah, sorry.
So it was not in terms of temporal formalization.
Okay.
So we consider it as integer, any value, and we iterate all potential. So basically we have 2 ranges, larger or less than that value.
Okay, that makes sense. Okay, great. Thanks so much. It looks like there is a little bit of follow-up discussion in the Slack about the boundedness. So if you want to follow up there, that would be great.
Sure.
So let's see, we're about out of time for questions. So let's go ahead and move on to the next speaker. So our next speaker will be Kay Lee, who will talk to us about deep SQLi. So Kay, if you can go ahead and share your screen and your slides.
All right, just a minute. So can you see my screen now?
Yes, we can see you. Yeah, there you go. Great, so you can go ahead and take it away.
All right, perfect. So hello everyone, my name is Kelly. I'm from the University of Exeter in the UK. Today I would like to share with you our recent work on the automatic test case generation for detecting SQL injection vulnerabilities. So our basic idea is to take advantage of the semantic information of the existing SQL injection test cases by using a neural language model to generate some new ones. So this work was carried out by my students in China and my colleagues in Northborough University, Tao Chen. And he's also in the Zoom today. So this is the outline of this talk. First of all, I would like to give you some gentle introduction about the background. Well, it is inarguable that we are in the connected world at this information age. So everything is connected via several physical systems and the Internet of Machines. Our daily life have been significantly benefited from those of internet companies. So this is the good news. But the bad news is the web applications are not safe, essentially, and they are vulnerable to a variety of security threats. So here is the statistics of the distribution of web attacks from different countries connected by the KMI. What you can see is like everywhere is a hotspot, very unfortunate. And here is another statistics. This is the breakdown of the proportion of different types of attacks happened during November 2017 to March 2019, also connected from KMI. So what you can see is that the largest amount of attacks are from the SQL injections, which is even 3 times than the second place. Well, actually, there are various ways to fight with the SQL injection attack. One is trying to protect the web applications from these attacks. So, for example, the input validation, where the software engineers manually set up some forbidden patterns or keywords to block those SQL injection attacks. But unfortunately, it's very difficult to enumerate all different kinds of attacks. Another one is the prepared statement not allow embedding user inputs as parameters. However, designing a effective prepared statement is never be an easy job, especially for those sophistications of defensive coding guidelines. And there are many other terms such as the dynamic SQL or DDL statement or table structures which cannot be parameterized. Well, another emerging technique is about using some artificial intelligence tools like a classifier to recognize those SQL injection attacks. On the other hand, well, in the software testing phase, actually, you can detect your SQL injection vulnerabilities of your system under test by using some test cases. There are some methods, either by using some manual methods or the semi-automatic tools to carry out the test case generation. But what we found is something missing in the literature, at least to our best of knowledge, is the AI-assisted tool that can proactively generate semantically related SQL injection attacks. And this is what we are going to do in this work. Well, our first argument is like the SQL is a programming language, and it is a language. Just like our human language, there should be some semantic information we can extract from those SQL statements. And such kind of a semantic information can help us to generate some more semantically meaningful test cases. And this is exactly the core idea of this paper. Let me just give you a simple example to have a taste about this idea. So suppose that we have a web application which has 2 input fields, very simple, just the username and the password. If we log these 2 inputs, and then we come up with the test case, which is actually a tautology attack. which means actually you can use any tautological clause to alternate this statement in a semantically equivalent or syntactically correct way. But once you want to formulate such kind of things, you have to follow some rules which can finally come up with the secret statement. And the other thing is, like, for example, if you want to have this kind of inputs, well, it looks like a test case, but actually many modern web applications can use their firewalls to trim such kind of things. But if you just replace those blank characters with a pass, then you may probably just disguise your system under test. Well, all these kind of things can be easily interpreted by the human software engineers, but it might not be easy for the machine to really understand that. So in this paper, we are going to leverage such kind of semantic knowledge to automate the test case generation process, and this is our deep CQD. Well, let's go straight to the design principles of our deep CQD. So this is the architecture. Essentially, it consists of 4 major steps. So the first step is going to train a neural language model by the transformer architecture. So once the model is trained, the deep CQD will use a crawler to automatically parse the web links of the SUT and find the injection points. Here we just use this particular tools provided by the Birdsuit project to do this job. And in the third step, actually we will use the trained neural language model to generate tokens with different probabilities leading to test cases. At the end, we will use those generated test cases in the SUT and to evaluate the effectiveness of this test case. So you may probably aware that there is a lie which is going to send the failed test cases back to the neural language model. So these kind of things make our new deep CQD a closed loop system. It does not really discard unsuccessful test cases which fail to achieve attacks as identified by the proxy. Instead, they are feedback to the neural language model to serve as a starting point for the retranslation. So this process has the potential to make our deep CQD become gradually more powerful in the self-improvement manner. So in the following, I will describe some important components in detail. So the first thing is about the language model itself, because this is the main crux of our deep CQD. So once we are talking about the language model, we have to talk about this one, the N-gram model, which is a very famous, popular one in the natural language processing field. So it is actually a joint conditional probability like this, and everything seems to be fine. But if you look at this kind of equation, we find that this kind of things will depend on the n+1 predecessor tokens, which means actually if you are going to predict the first token in your sequence, then you may probably don't really have your predecessor and your whole thing will screw up. But if you use a neural language model, probably you can mitigate such kind of issues. In deep CQD, actually, we use a particular structure which is called the multi-head self-attention in the neural language model, because these kind of things can learn a more diverse representations by concatenating multiple independent self-attentions. And this is actually the working flow of our encoder and decoder model, which is a sequence-to-sequence model in the deep CQD. In our work, actually, we use the transformer framework to train or to build our sequence-to-sequence model. Well, it's kind of complicated, so I don't really want to elaborate this one here. But one thing we need to mention is like the neural language model can learn the semantic knowledge of the SQL attacks independent to the actual web application. And such kind of a learned knowledge can also be generalized to other SUT. Well, when we are going to talk about the training of your neural language model, we have to develop, or we have to define what it looks like as a training data. So it is actually an input-output pair like this. But if you want to formulate a valid training data, you have to follow the following conditions, at least one. So the first one is like probably your input is a normal user input, which is a benign one, but you want to have a B, which is a test case, which means like this is a malicious test case, malicious input. Or both A and B are different kind of test cases, but conform to the same type of attack. The third condition is like A is the test case and B is just the extension, which makes it more complicated or become another type of attack. So this is the condition. Based on these kind of conditions, we can manually create the input-output test cases, test case pairs to build up our training data set based on some publicly available SQL test case repositories. There are two steps we're going to do. So the first step is to mine the repositories of fuzzing test or brute force tools from various GitHub projects. So we share this kind of information from this Dropbox link. After that, we will use 5 different mutation operators to further exploit the test cases obtained from step 1 in order to obtain some semantically similar test cases for disguise attack. So this is a list of the description of 5 different mutation operators. Probably you can find more details from that from my paper, but I want to give you the idea why we want to do this. It's because actually you have your SAT may probably have some firewalls or input feeders which can train some of the test cases like this. But if you change it to this one, it works. So I think the reason is because the rare existence of semantically similar SQL attacks based on manipulating some synonymous or encoding formats from those public repositories. And this is exactly what we want to do by using the mutation operators. So once you have the training data, then you have to pre-process that for a better training purpose. So by using the generalization or word segmentation. Here we only generalize the user inputs, the table name, the column name to some unifying tokens, like the normal table or column. And at the end, we will train the model by using ADAM, which is a stochastic optimization algorithm. We will use the 10-fold cross-validation in the training process and to tweak some hyperparameters. And this is the loss function we use in our training process. And well, once you have your neural language model, then you can use that to generate the test cases. But one thing you have to keep that in mind is like it is different from machine translation, which you are only interested in the most accurate sentence that matches the semantics. So that you just take the tokens have the highest probability. But in deep CQD, our purpose is to generate as diverse test cases as possible, so that more bugs and vulnerabilities can be identified. To this end, we use the bin search to extend and guide the neural language model to generate a set of semantically related test cases. So its basic idea is to select m most probable tokens at each time step, given all previously selected tokens, and to leverage the neural language model to carry on the search from these m tokens and just discard the other ones. Here, the m represents the bin widths, and we set m to be 5 in our experiments. So this is just a simple example. So what you can see is like, given the input token all, so probably have 5 different outputs from your neural language model. And O1 and O2 have the highest probability. Then in the next step, we will start from these 2 to generate 5 more different test cases and so on and so forth. By doing so, we can expect that we can have a more diversified test cases at the end. So I think that's pretty much about the deep CQD, which is kind of different from the literature. So then we move to the empirical study. We will simply introduce some of the setup of our experiments. So first of all, we compare and evaluate our deep CQD with another penetration testing tool, SQL Map. And we use 6 SUT written in Java with MySQL as a backend database in our experiments. And we use the rules that we introduced before to pre-process our training data set and mutate our training data set to, at the end, have like more than 56,000 CQ injection test cases as the training data. And we use these 3 column metrics to evaluate the performance. So let's look at the results. So the first research question is quite straightforward. So we are just going to see that whether the deep CQD effective for detecting CQ vulnerabilities. So this is the a bar chart of the ratio of the average number of vulnerabilities identified by the deep CQD and that versus that of the no vulnerabilities. So what you can see is that in most of the cases, the deep CQD can identify all those no vulnerabilities except this one, events system. So I think it is because the coroner cannot really identify all those injection points for the events system. And the other thing that you may probably need to be aware is like for this and these SUTs, what you can see is like the deep CQD can identify more vulnerabilities than you already know before. So this is remarkable because it means that the deep CQD is able to identify some previously unknown and deeply hidden vulnerabilities over the underlying black box SUT. So to further understand why deep CQD is effective for revealing the CQ vulnerabilities, this table just shows you some injectable CQ statements and the related test cases generated in our experiments. Well, I don't really want to elaborate that all of these kind of cases, just to give you some the sense about the first example. So deep CQD is able to learn that the input case is not successful because you may probably just miss some quotation mark. They generate another semantically related test cases, which finally formulate a test case at the end to inject your system. So from these experiments, we can answer the first question. In short, deep CQD works. And the second question is about whether the deep CQD can outperform the CQ map for detecting CQ injection vulnerabilities. So this is a comparison of the ER value, which is the ratio between the successful test case and the total test case. What you can see here is like the number of test cases that are used in the deep CQD is significantly smaller or fewer than those in the CQ map. But the ER or the successful rate is higher than those you can have in the CQ map. So which means deep CQD can better utilize the test resources. And this is a violin charts of the number of CQD vulnerabilities identified by the CQD and CQ map, or deep CQD and CQ map. What you can see is like in all cases, actually, the deep CQD is better than those CQ map. And the other thing is like you can see that the variance of deep CQD is very small. So which means the deep CQD is also robust in the sense. And this is the comparison about the CPU time that carried out by the deep CQD and the CQ map. What you can see is like a deep CQD runs much faster than the CQ map. And especially in the Porter case, what you can see is 6 times faster than CQ map. So I think one of the reasons is because CQ map generates many more test cases than the deep CQD, but most of the test cases are useless, which makes it much slower than this deep CQD. So the second question can be answered is like deep CQD is better than CQ map on the 6 SUT. And the last question is about the level up of your system. So in the previous experiments, we just set up the input validation to be essential level. And in this experiments, we just level it up to the advanced level, which is more complicated than before. So this is the results. So what you can see is that even though you make your system to be more secured, but the deep security is also able to find out more vulnerabilities than SQL map. And one thing is interesting is like for these class fields and office talk, what you can see is like SQL map cannot really find any vulnerabilities once you have advanced input validation. And well, this is actually a cross comparison of some previous experiments, but what you need to look at is just the last figure. So this figure is going to say, once you level up your security level, so what happens is like, you may probably see that a reduction of the number of vulnerabilities identified, but which one is more significantly affected? So what you can see is like the number of reductions achieved by the deep security is smaller than the SQL map, which means the deep security is less affected by the strengthened input validation. So the last research question can be answered is just like, even though you level your input validation, deep security still outperform SQL map. So at the end, actually, I would give a very short conclusion about our contributions. So we propose a fully automatic and end-to-end tool empowered by the tailored neural language model trained by the transform architecture. And we propose some methods to make our data sets to be more diversified and our test case to be more diversified. And the effectiveness is validated on 6 reward SUT. I think the uniqueness of our deep security is like it is not only able to translate or a test case to another test case. It can also translate a normal user case inputs to a malicious one. And deep security is a closed loop system that can improve itself from some unsuccessful test cases. So I think that's all about my talk, and thank you very much for your attending. So any question can be welcomed here.
All right, thanks, Kei, for a good talk. So we're actually a little bit over on time, so I want to be aware of that. But what I would, I guess, suggest is that if there are questions, you can post them in the Slack, and possibly Kei can answer them there. But I want to go ahead and end the session since we are over on time, and point out that the next session will be at 2:50 on regression testing. So again, take up any conversations in Slack.